Welcome back. So today we're going to talk about the topic of loop parallelism. So the overall goal of this lecture is to create a methodology for designing algorithms in the shared memory setting. Okay, so this is similar to what we talked about last lecture, where we talked about Foster's methodology and how to design algorithms in the distributed memory setting. Okay, and the reason we're talking about loop parallelism is that most of the parallelism in shared memory programs happen within loops. Okay, so if we want to design efficient shared memory algorithms, we're going to focus on how to efficiently parallelize loops. Okay, but before that, let's first go over the overall methodology for designing a shared memory algorithm. Okay, so this is similar to Foster's methodology, where if you remember, the steps in Foster's were that you first partition the problem, so you break it into many subproblems, right? And then you group some of these subproblems together, you agglomerate them, right? And you find the communication between the subproblems, and then you group the subproblems together, and then you map it onto your processors. Okay, so in the shared memory setting, we're going to go through a similar set of steps. Okay, so our first step is to basically take a big problem, the original problem, and then break it into a bunch of subproblems. So we're going to find what tasks there are in the original problem. And we're also going to look for the dependencies between the tasks. So basically, we want the tasks to be independent, or mostly independent, because we're going to map them onto different threads later. Right? And the threads are not able to efficiently synchronize with each other. So therefore, if there's a lot of dependencies between the different tasks, right, then you're going to get very poor efficiency because you're going to have to add a bunch of synchronization operations like barriers between the threads, right? So that's going to really hurt your performance. So if we don't want to have a lot of barriers, then we want the tasks to be as independent as possible. Okay, so we want to break the big problem into a bunch of tasks which we hope are independent. Okay, and then after that, we're going to map these tasks onto threads. And during this mapping process, you have to be careful about things like load balancing. Right, and then finally, once we have the mapping, then we can just convert that into a program that we can run on a shared memory computer. Right, and so for that, we're going to just use OpenMP to do this. Okay, so so that's the overall design process. Now, there are several things we need to keep in mind when we do this. We're going to take our original program and then break it into these tasks, and the tasks. All of the statements within the program, okay, there's some sort of dependency between these different statements. And so we said that we want the tasks to be independent. And so therefore, we need to figure out what is the dependency between the different statements. And to do that, we're going to use something called dependence analysis, okay, which I'll show you later on. Okay, and then using this dependence analysis, you can determine what kind of tasks you want to form. Right? You want to form independent tasks. Okay, and once you've done that, now you can take your independent tasks and then you can map them onto processors. And when you do this, one of the big things is to load balance. Right? So, for example, we looked at methods in OpenMP to load balance, for example, using static or dynamic allocation of the work, right? Or using a block or cyclic allocation of the work. We also need to be concerned about things like shared versus private variables, okay? Because if you share a variable that you aren't supposed to, right? Then you're either going to have a bug or you need to put like locks around these variables, but then that's going to hurt your efficiency. Okay, so if possible, you want to make variables private so that the different threads are not going to collide with each other. Okay. Also, we saw some examples when we talked about OpenMP where if you want to do some sort of collective operation that involves some sort of synchronization, like you want to add together a bunch of numbers, right? You can either do that using shared variables, but then you have to protect these shared variables, or you can use something like these reduction variables, which are much more efficient. Okay, so we need to think about how we specify the different variables to achieve both correctness and efficiency. Right, okay. And then we also want to think about things like if we're working with data structures like matrices, we want to think about whether we want to map these row-wise or column-wise. Okay, so that can also affect performance because of like cache use, for example. Okay, so so our first thing is to figure out what kinds of tasks we can create. Okay, so we need to create independent tasks, and how do we tell whether tasks are independent? So we're going to use this technique called data dependence analysis. Okay, so so this technique is basically letting us determine whether statements in a program can be executed in different orders. Okay, so suppose you have a sequential program, and let's say that you have two statements in that program, okay, S1 and S2. So let's say that S1 occurs before S2 in the sequential program. Okay, now S1 and S2, there could be dependencies between these statements, or they can be independent. Okay, if the statements are independent, then we actually don't need to keep them in the order S1, S2. So currently, they occur in the order S1, S2 in the sequential program, right? But if the statements are independent, then we could actually swap their order. So you could do S2 first and then S1. However, if the statements are dependent, then you have to do S1 before you do S2. Okay, because if they're dependent, then if you swap the order of the statements, you can actually get a different outcome for the program. Okay, so we need to make sure that, right, whereas if they're independent, then even if you swap their order, you get the same outcome and same output from your program. Okay, so we need to make sure that anything that we do to the program, any transformation or parallelization, right, that's going to maintain the same output as the original sequential program. So therefore, if these statements are dependent, then we have to make sure that they execute in the order S1 and S2, even when you parallelize. Okay, so now what kinds of dependencies can there be between these statements? Okay, so there are basically three types that we're going to look at. So the first one is called read after write dependence, okay, or a true dependence. And the way we're going to write that is we're going to write this S1 and then arrow T S2, okay, and the T indicates that it's a true dependence. And basically what this means is that S1 is going to write to a memory location, and then S2 is later going to read from that memory location. Okay, so then S2 has to happen after S1 because you know, S1 writes a value and then S2 reads it later. Now, if you were to switch the orders of these operations so that S2 reads this location first and then S1 writes it, right? Then S2 could get a completely different value. Okay, and then the program can behave differently. So we said that you know, if you want to reorder these statements, you have to make sure that after the reordering, the program behaves the same way. Now, if there's a true dependence, right, then we see that we cannot reorder and still guarantee that the program behaves the same way. Okay, so if there's a true dependence, then we have to make sure that S1 is always going to execute before S2. Okay, another type of dependence is called anti-dependence, or WAR, which stands for write after read. Okay, so this is where S1 reads a location, right? And then later on, it's written by S2. Okay, so this is different from the read after write, because read after write is you first write to a location, and then later S2 reads from that location. Okay, so here for the anti-dependence, it's that you first read the location, and then somebody else later writes to it. S2 writes to it later. Okay, but in this case, again, you have to make sure that S1 executes before S2. Okay, because for example, if you read, if you run S2 before S1, right, then S2 could write a different value than the current value in that location, right? and then in that case, if you do S2 first and then S1, S1 can get a different value. Okay, and the third type of dependence is the write after write dependence. Okay, this is also called an output dependence, right? And then this is indicated by this arrow with the O. Okay, so this is basically where S1 and S2 both write to the same location, same memory location. So again, you have to preserve the order of these two statements, because if currently you're writing S1 and then S2, right? But if you switch the order, then of course the that memory location is going to end up with a different value at the end. Okay, so because we need to we need to guarantee that any kind of reordering preserves the behavior of the sequential program, then we cannot reorder these statements if they have this write after write dependence. Okay, so these are the dependencies that we have. And if the statements do not have any sort of dependence, okay, if they're not read after write or write after read or write after write, right, then we say that they're independent. And if we have independent statements, then we can actually execute them in either order, right, and it will not affect the outcome or the output of the program. Okay. All right, so let's do some examples. So suppose you have these 5 statements over here, right? So they're just they're assignment statements, or they read from a location and then they do some sort of assignment. Okay. So now, what kinds of dependencies do we have? Well, for example, we have a true dependence from S1 to S3. Okay, so this is a true dependence because here X reads. So we first read the value of X, okay? We first write to the value of X, okay? So we write 2 to the value of X, and then later S3 is going to read X, okay? So that's a read after write. Okay, so that's a true dependence, and you can see here that we cannot swap the order of these two statements, because so let's say that initially all of these variables are 0. Okay, so X, Y, Z are all 0 in the beginning. Okay, so then you see that if you do them in the current order, S1 and then later S3, right, then Y is going to become 2 at this point, right, and X and Y are both 2 at this point. Okay. However, if you switch the order of these statements, okay, then because X is initially 0, right, then Y is going to become 0, and then X is going to become 2. So you see that doing these statements in the order S1, S3 is different than doing this in the opposite order. And this is why you're not allowed to switch the order. Okay, so that's one example of a true dependence. You also have another true dependence. So for example, we have, let's see, all right, so we have a true dependence from S2 to S4 because in S2 you write to memory location Z, right, and then in S4 you read from Z, Z, and also X. Okay, yeah, and again you see that if you switch the orders of these statements, you're going to get different behavior. All right, another example, so let's say, right, so we have an anti-dependence from S4 to S5. Right, okay, yeah, so we have an anti-dependence from S4 to S5, right, and this is because, we first read the value of, read the value of Z, right, into Y, and then later you write the value of Z. Okay, so that's a write after read. And then, okay, and then lastly, we have some output dependencies. So for example, we have an output dependence between S2 and S5. Okay, so they both write to the same memory location, and if you switch their order, then you're going to get a different value for Z. Okay, so this is how we're going to do, we're going to find dependence statements. Okay, we're going to look to see if they have a true, anti, or output dependence. Okay, yeah, so this statement just summarizes what I've been saying, which is that if you parallelize a program, okay, then you have to make sure that dependent statements are going to run in the same order in both the sequential and the parallel version. Okay, and then that's how you guarantee that both the sequential and the parallel programs have the same behavior. Okay, if you don't satisfy this condition, right, then when you run your program, sometimes you might get the correct behavior, right, but this is not guaranteed. Okay, so we want a completely solid guarantee that we have correct behavior when you parallelize. Okay, so the parallel program must maintain the same dependencies as the original sequential program. Okay, now this dependence relationship, this is actually transitive. Okay, so this means that if S2 depends on S1, okay, and S3 depends on S2, okay, and this can be any sort of dependency. It can be the true dependency or the anti or the output dependency. Okay, but if there's some sort of dependency between these three statements, right, then S3 is also going to depend on S1. Okay, so this basically means that S1, you have to run S1 first, and then S2, and then S3. Okay, when you parallelize. Okay, so a consequence of the statement that we have to make sure that dependent statements run in the same order, a consequence of this is that if you have dependent statements, you cannot run them on different processors. Okay, because if you have two dependent statements and then you run them on different processors, there's no way that we can guarantee, or actually there's no cheap way, okay, that we can guarantee that they're going to execute in the right order. Okay, you could use some very expensive mechanisms to sort of ensure the relative ordering. Okay, but those cost so much that we don't want to use them, and so if we don't use those expensive primitives, then we have no guarantee that these two statements are going to run in any particular order. Okay, so for example, if you have a statement, let's say you have a statement S1, right, and there's some sort of dependency to S2, right? So now if you have two processors, P1 and P2, right, and they run, you give one statement to one of the processors and the other one to the other one, right, then because these processors can run at different speeds, okay, then when you execute this thing in parallel, sometimes you might get that S1 runs before S2, right? In that case, you might get the correct behavior, but sometimes you might get S2 runs before S1, okay, and then you might not have the correct behavior. So therefore, if these two statements are dependent, right, then you have to put them onto the same processor, right? Either put both of them onto S1 or P1, or both of them onto P2. Okay. So so when you have dependent statements, you don't get parallelism, okay, because you have to run all of them on the same processor. Okay, so then in order to get parallelism, what we want to do is to find independent statements. Okay, so we want to find statements where you do not have any dependency. Okay, in that case, when you have independent statements, then you can indeed run them on different processors. Okay, so our goal basically, in order to get good performance for shared memory programs, is to find as many independent statements as possible. Okay, and in fact, when we do this, we're going to focus on finding independent statements in loops. So we're mostly going to focus on parallelizing loops. Okay, and the reason for doing this is because if you look at most shared memory programs, most of the computation is happening in some sort of loop. Okay. So so if we can get good performance on these loops, then we can probably get good performance overall. Okay, so we're going to use some notation when talking about loops. So for example, let's let S be a statement in the program. Okay. Now, if S is occurring inside of a loop, right, then the loop has a bunch of iterations and iteration variables. Okay, so for example, if you have if you have a nested loop, right, you might have iteration variables I and j. Okay, so then we're gonna write this notation over here, S square bracket ij, to denote the execution of statement S in the iteration ij. Okay, so however many loop variables you have, right, iteration variables, okay, we're going to write S, and then we're going to list out the iteration variables, and that's going to denote the execution of the statement S in some particular iteration. Okay, so now we're going to look at, so previously we talked about dependencies between statements. Okay, so now since we're trying to parallelize loops, we're going to look for dependencies between statements in different iterations of a loop. Okay, so this is going to be called loop dependence analysis. So, so we have different types of dependencies between statements in loops. Okay, so one is we have something called a loop carried dependence. Okay, so this means that we have dependencies across different iterations of the loop, right? So maybe like a later iteration depends on a previous iteration. Okay, so it's carried through the loop. And then you also have something called a loop independent dependence. Okay, and that's actually saying that you have some sort of dependency, but it's within the same iteration of the loop. Okay, so some examples of this. So suppose you have, let's say some code like this, right? Then, so here we have 3 different for loops. So in the first for loop, right? If you look at this statement over here, S1, then you actually have a loop carried dependence. Okay, between iterations I and I plus 1. So we have a true dependence between iteration I and iteration I plus 1. And the reason for that is because, so this is going to be a read after write dependence. And so what's happening is in iteration I, we are writing to location AI, right? And then in iteration I plus 1, we're again going to execute the statement S1. And when you execute it, when you do this part, right, then because we're in iteration I plus 1 now, so then what we're looking at here is actually I plus 1 minus 1, okay, which is of course I. So this means that in iteration I plus 1, we're going to be reading from A of I. Whereas in iteration I, we're writing to A of I. Okay, and because iteration I plus 1 happens after iteration I, then this is a read after write dependence. Okay, we read A of I in iteration I plus 1 after you write A of I in iteration I. Okay, and this is across 2 different iterations, so it's a loop carry dependence. You also have a loop independent dependence because here, even within the same iteration, okay, you have a true dependence between statements S1 and S2. Because, for example, in S1, you're going to write to A of I, right? And in S2, you're going to read from A of I. So that's a true dependence, a read after write. Okay, now let's do another example. So in the second example here, right, second for loop. So here we have a, let's see, we have a loop carry dependence from, so we have 2 loops here, okay? So we have a loop carry dependence from now this S3 of ij, right? So this is talking about the execution of the statement S3 in the iteration I comma j, okay? And there's a true dependence to the same statement, but in iteration I j plus 1. Okay, and the reason is that in iteration ij, we're gonna write to A of ij, right? And then in iteration I plus 1, right, we're going to do this, in iteration j plus 1. Okay, same I, but we increase j. Right, so in that case, in iteration I j plus 1, you're going to be reading from I, and then this is j plus 1 minus 1, so that's A of ij again. Okay, so yeah, so we first write to A of ij, and then in the next iteration, next j iteration, we read from A of ij. So therefore, there's a loop carry dependence in the j loop. Okay. However, you see that there's no loop carry dependence in the I loop. Okay, because for the I loop, right? Yeah, I mean, when you go to the next value of I, right? You're just looking at for any value of I, you're just looking at values of A of I and then some sort of j. Okay, you don't carry, but you don't look at values from A of like previous I's. So therefore, there's no loop carry dependence in the I loop. Okay, and then in this final example here, right, in the third example, we have a true dependence from in the I loop, okay? Because here you're writing to A of ij, and then for the next I loop, right, you're going to read from A of ij. However, there is no loop carry dependence in the j loop, okay? Because for every value of j, you just look at, you always look at a single value of j in statement S4. Okay, so now we're gonna introduce a sort of a few sort of ways to help us look at dependency and independencies. Okay, so there's sort of tools to help us with our dependence analysis. So the first one, we're going to create a graph to represent the various dependencies or iterations between the iterations of a for loop. So the first one is going to be called the iteration state traversal graph, okay, or ITG. And this is so this graph just shows the order that we step through all of our iterations of our for loop. Okay, so so what this means is, so I'll just show you an example of this. Okay, so if you have a loop of this sort, right, then you have a bunch of iterations, right? So we have iterations for I and j. Okay, so now we're going to create node for each. We're going to create one node for each iteration of this loop. Okay, so in total we have like you know, we have n squared iterations in total, right, for different values of I and j. Okay, so our iteration traversal graph is going to have one node for each of these iterations. So it's going to have n squared nodes. Okay, and then we're going to create edges between iterations that, so the edges will indicate which iterations have to come after another one. Okay, so the edges basically give the order of traversal of this loop. Okay, so so if you look at this loop, right, you have the outer loop I, and then you have the inner loop j. So therefore, we're first going to go through all of the j iterations. We're going to fix a value of I. We're going to go through all of the j iterations for that I. And then we go to the next I, right? And then we go through all the j iterations again. So therefore, the order that we iterate through is we take the first value of I, we go through all of the j values, right? And then the next I, we do all the j values, and then so on. Okay, so yeah, so that's so this is going to give us our iteration traversal graph. Okay, we're going to create an edge between two consecutive iterations in the ITG. Okay, we're also going to have something else. So this is called the loop carry dependence graph. Okay, so this graph is actually going to show the dependencies between these different iterations, right? So the ITG showed the order that we iterate through, and then the loop carry dependence graph is going to show which of these iterations actually depend on which other ones. Okay, so yeah, so this LDG is going to show us all of the true or anti or output dependencies. Okay, so in the LDG, again, we're going to create nodes for all of the iterations of the loop. Okay, and then now the directed edges are not, they don't represent the order of execution anymore. Rather, they represent whether there are dependencies between different iterations. And so, yeah, and so if we form this LDG, then we can determine from the graph where the dependencies are. Okay, so as an example, suppose you have this loop over here, right? So this loop, we see that there is a loop carry dependence in the j loop, right? And then there's no loop carry dependence in the I loop. Okay, so to represent this in the LDG, what we're going to have is, so we have nodes for every iteration, right? We have a node for every iteration, okay? And since you have a loop carry dependence in the j loop, right, then you see that, you know, for each fixed value of I, right, then if you look at one value of j and the next value of j, there's going to be a true dependence there. Okay, so we're going to make an edge there, and you can label that with T for the true dependence. Okay, so this, so we have true dependencies between all consecutive iterations of j for each fixed value of I. Okay, so that's where all, so these edges basically are because of this over here. Okay. However, because there's no loop carry dependence in the I loop, right, then for these different values of I, we don't have any edges between between any of these nodes for different values of I. Okay, so yeah, so that's the LDG, And basically, once you have this LDG, okay, then you can use it to tell you how you're going to parallelize your program. Okay, because when you parallelize, you have to make sure that all of the dependent statements stay on the same processor or the same thread or something. Okay, so for example, you have to make sure that this row of statements, okay, this is all got to be mapped to the same processor. Right? That's the only way that you can guarantee that these statements are going to execute exactly in this order j equals 1, 2, 3. Okay, and likewise for the second row, right, you have to map those also onto the same processor, and same for the third row. Okay, however, you don't need to necessarily map the first row and the second row onto the same processor, because there's no dependence between any of the statements in these two rows. Okay, so even if you map them to different processors, right, then so these could execute in some weird interleaving now, right? So maybe this one, maybe this one goes first, right, and then that one, right, and then maybe you have that statement and then that statement and then these two, right? But this is fine, because all we need to do is to guarantee that this statement executes after that one, right, and this one comes after that, right, and then same over here, and we've guaranteed that. And so it's fine if we don't really care about the interleaving between statements like this or these statements. Okay. All right. So this basically indicates that for each connected component of the LDG, okay, connected component is that you have these nodes and they all connect to each other. These all have to get mapped onto the same processor. Okay, and this has to get mapped onto the same processor, and then so on. However, different connected components can be mapped to different processors. And that's where your parallelism comes from. Okay, you can map these 3 rows onto 3 different processors, so you can get like 3x parallelism. Okay, so that's the basic idea. Now let's do some examples of this. So first of all, we're going to have a loop like this. Right. So in these examples, the first step is always to find out what the dependencies are, right? Both the loop carry dependencies and the loop independent ones. So for the loop carry dependencies, so let's see. So we have some true dependencies in this loop, right? Because we have a let's see. So here you're gonna read from let's see. Yeah, sorry. Here you're going to write to A, and then here you read from A, right? Okay, so there's a loop carry dependence over here, and then this is also a true dependence. Okay, so that's we have one dependence over here. Now we also have an anti-dependence, because here you read from B, right, and then here you write to B. Okay, so there's also an anti-dependence. But this is within the same loop, so it's a loop independent dependence. Okay, and for output dependencies, we don't have any. Okay, so those are all of our dependencies, and now we can draw these ITGs and the LDGs, right? And so for the ITG, we're going to iterate through the J iterations first, right, and then the I iterations. And then for the LDG, well, we look for all of the loop carry dependencies. Okay, so the only loop carry dependence is over here, and this is in the J loop, right? So so we have these dependencies in the J loop, right? And then for each I, we have some loop carry dependencies in the J loop, but we don't have any dependencies in the I loop. Okay, so if you look at all of these dependencies, right, none of them involve the I loop. And so therefore, our LDG is going to look like this. And so we have 3 components in this LDG, right? And so each of these components can be mapped onto a different processor. Okay, so in general, you would have n components, right? You would have one component. Each of these rows would be a component, right? So every different I leads to a component. Okay, so yeah, so therefore, now remember, the overall design process for the shared memory program is that first of all, we're going to create these tasks. Right? We're going to start with a big program, and then you're going to break it into these tasks that can be run in parallel. Okay, and then later on, you're going to map the tasks onto the processors. And so therefore, our tasks, since you want the tasks to be independent, right? So what we see is that the independent tasks are for each I, we have an independent task. Okay, so that's what we're going to do. We're going to create n parallel tasks, one for each I. Okay, okay, so then the next step is once you have these tasks, right? So we have n tasks, but you might only have, less than n processors. Let's say you have p processors. Okay, so then now we need to map all of these tasks onto the processors, and then one of our goals is to maintain load balance. And the way we can do that, so here, so each task is just one of these rows, right? So it's all of the iterations of the J statement. Okay. And all of these tasks actually have the same size, right? Because each of these rows does the same number of iterations of J. Okay. So that makes the load balancing problem easier because we can just assign the same number of rows to each processor. Okay, we have a bunch of rows and a few processors. We're going to assign the same number of rows to each processor. So for example, you can use something like a static mapping in OpenMP. Okay, so now we can actually write a simple OpenMP program to represent this loop, right? So we start initially with just these two for loops, and to parallelize in OpenMP, you just write these pragma OMP statements. Okay, so here we're trying to parallelize the for loop, so we're going to create a parallel for over here, right? Now this private J is, so this parallel for is only going to parallelize the outer loop, okay? Because we said that the parallel tasks are among the different I's. Okay, so the parallel for is going to parallelize different iterations of the I loop. But it's not going to parallelize the J loop, so the J loops are still going to run sequentially. Okay, and that's what we need because we have these dependencies between the J iterations. Okay, now when you parallelize, you have a bunch of different processors, and you want each of them to do its J loops separately. Right? So that's why you need each processor to have its own private copy of J. So that's what this private thing is saying over here. Okay, every processor gets a different copy of J. Okay, otherwise, all the processors would share the same copy of J, and that is a problem, right? Because these processors are iterating through J at different speeds. So they cannot. So you don't want to have just one common value for J. Okay, we're going to use a static schedule here. So that's basically going to give the same number of I iterations to each processor. Okay, it's going to give n divided by p to each processor. All right, so next let's do another example. So here we have a for loop like this. Okay. Now, again, the first step is to find out what all the dependencies are, right? So here the dependencies are between, so there's a true dependence from statement I to I plus 2, okay? And that's because, in iteration I, you write to A of I, but then in iteration I plus 2, you're going to read from A of I, okay? And there are no other dependencies. Okay, so now let's form the ITG and the LDG. Okay, so the ITG is, well, since you only have a single for loop here, then the ITG is just a line like this. And the LDG is that, well, we have these, so we have all of these iterations, right? A bunch of iterations of I, and because of this true dependence over here, right, from I to I plus 2, then this means that there's a true dependence from 1 to 3, right, and from 3 to 5, and so on. Okay, 5 to 7, and so on. And also there's a true dependence from 2 to 4, and 4 to 6, and so on. However, there is no dependence between iterations like 1 and 2, or 3 and 4. Okay. Yeah. So so this LDG shows all of the iterations. All of the dependencies that we have. And now we said that the tasks are basically going to be the connected components of this LDG. Okay, so we see that we have two tasks. Okay, one for all of the odd iterations, right, and then one for all of the even iterations. Okay, so so we can get some parallelism because at least we don't have any dependencies between the odd and the even iterations. Okay. And so, so therefore, we're going to form two tasks, right? And then, So since you only have 2 tasks, we're not going to parallelize a for loop. Instead, we're going to use sections. Okay. So remember that the way sections work is that if you write pragma OMP parallel sections, then you can create a bunch of sections. Each section is a block of code, and each section will be given to a process, and the different sections can be executed in parallel. Okay, so here we have 2 sections that can be executed in parallel, right? One is the even iterations, and the other one is the one is the odd iterations, and the other one is the even iterations. Okay. Right, and then we need to say that these 2 parallel threads that we have, right, one for this one section and one for that section, they each need to get their own copy of I, okay, because they're iterating through the for loop independently. Okay, so another example, so here we have a program like this, okay, so it's again just a single for loop, and then we have a statement of this form. And now if we're going to look for the dependencies, and you see that there is a dependence, in fact a true dependence from true loop carry dependence, okay? Because here you write to AFI, and in the next iteration you're going to read from AFI, right? So here you're going to read from AFI in iteration I+1. Okay, so then now we're going to form the ITG and the LDG. Okay, so the ITG is like this. And the LDG is because you have a loop carry dependence from iteration I to I+1, right? Then you have just a single component here, right? You have a line to for the LDG. Now in this situation, it looks like we don't have any parallelism, okay? Because we said that we can only run different parts of the graph if they are in different components. And here there's just one component for the graph. Okay. However, if we take a look at this code, okay, so we see that this code has like sort of several parts. Okay, so well, actually let's go back to the code. Okay, so we're doing some computations. So if you break this code into 2 parts like this, okay, you see that the only dependence is between this A part over here. Right. Now for the B part, right, there's no dependence for the for the other part, okay, involving B, C, and D. There's no dependence there, right? Because on the we don't have anything involving B, C, and D on the left-hand side, okay? Right. So so actually we do need to do all of these A iterations in sequence, in order, right? Iterations 1, 2, 3, 4, and so on. However, all of these other iterations involving B, C, and D, right, they're all independent of each other. Okay, so we don't necessarily need to do them in order 1, 2, 3. Okay, so because of this, we can actually take this loop and then break it into 2 parts. Okay, so this is called loop fission, right? Fission is like breaking apart things. So, and then now we can take the single loop and we can distribute it into 2 different loops. So if we do something like this, okay, so the top part here is the second part of the loop, right, involving BCD. Okay, and what we're going to do is we're going to do all of these iterations, but we're going to store these results in these temp variables. Okay, yeah, so we have a temp array over here, and then also for the iterations involving A, right, we're going to do these in order, and then we're also going to add in the values from the temp array. Okay. All right, and now what you can see is that if you look at the different iterations of the first for loop, right, there are no dependencies between these different iterations. Okay, you can do them in any order. All right. Whereas, sorry, talking too much today. Whereas in the second for loop, we do have loop carry dependencies. Okay, so you have to do them in the order like 1, 2, 3, and so on. Okay, so that tells us that we can try to parallelize the first for loop, right? But we cannot parallelize the second for loop. Okay, so now let's go ahead and do that. Okay, so we're going to write an OpenMP program to parallelize the first part. Okay, So we have parallel for over here, right? We have a static schedule, and we can run all of these iterations of the first for loop in parallel. For the second for loop, right? So this is now outside of the parallel for section, right? And so this is going to execute sequentially. But at least we got some sort of speed up overall, right? Because previously you executed all of the statements sequentially. Okay, and now you're going to execute like half the statements in parallel. Okay, so another way to look at this is that if you say each of these statements, right, the BCD part and the A part, let's just for simplicity say they each have a cost of 1. Okay, then if you do n parallel loops, right? If you do n loop iterations of the loop overall, then the sequential cost will be 2 times n, right? Because each iteration you do this part, which we assume has a cost of 1, and the A part, which has a cost of 1. So the parallel running, the sequential running time is going to be this, okay? Whereas the parallel running time, right? Because you can do the first part in parallel, then we're doing n iterations of this in parallel, right? But you can parallelize across p threads. Then the first part only takes n divided by p time, and the second part still takes n time. Okay, but you see that you're getting some sort of speed up here, maybe up to almost a factor of 2 if you have lots of parallel processors. Okay, so this is still worth doing. Now, one problem with this is that here we stored all of these different B, C, and D values, right? We stored them in this temp array. Okay, so we have n values for this temp array. So that's kind of like we need to store more things. So that's storage overhead. Okay. Okay. So a way we can actually deal with that is that we can we can do something like this. Okay. So sorry, there's a little problem over here. We should actually do it this way. Okay. Now, what this is saying is that we're gonna now just create one big parallel for. Okay. And we're going to have these statements, the BCD statements over here. And the parallel for, if you have p threads, it's going to, what we're going to do is create p copies of this private variable t. Okay, so each thread has its own copy of this private variable t, right? And then after that thread computes this value, right, the B, C, and D stuff, it's going to write that into t. Okay, and then but all this is being done in parallel. However, we know that we need to do the A loops in order. Okay, so in order to do that, OpenMP actually has a statement called ordered, right? So the ordered statement, when you write this ordered statement within a for loop, that's going to force the execution to do these iterations in order of I. Okay, so we know that we need to do this for the for loop on the A in the order of I. And so by adding the statement over here, we get that behavior. Okay, right, and and the advantage of doing it this way is that now each thread just has one copy of this variable t, right? And so yeah, so in total, if you have k threads, right, then you're just using k amount of extra storage. Whereas for the first example, right, if you have n items, then you're going to use n extra amount of storage, right? And n is usually much larger than k, and so this second method is going to save time. Okay. Now, also, I need to say that so here the reason I changed this schedule here was yeah. So previously, you don't want to run this on a static using a static schedule. Okay. Rather, you want to run this using something like a static schedule with a chunk size of, let's say, 1. Okay. So if you remember how this works when you use a chunk size of, let's say, 1, what you're going to do is you have a bunch of iterations of this for loop, right? And so so let's say that you have 3 threads. Okay, so you have threads 1, 2, and then 3. Okay, so the static schedule with a chunk size of 1 is going to assign these iterations to the threads 1 at a time, right? So a chunk at a time, and chunk is 1 here. Okay, so that means that you're going to give the first iteration to T1, right, and then the second one to T2, and then 3. Okay. And then iteration 4, you're going to go back to T1, and then 5, and then 6, and then so on. Okay? Oops. Right. And the nice thing about using a chunk size of 1 is because now we have to do these A statements in order. Okay. And if you do a chunk size of 1, right, then you basically you have that T1 is going to run first, and then T2, and then T3. Okay. So right, and what they're running is they're basically so they first need to do this statement, right? So they can do let's call this statement S1, okay? And then here let's call this S2, okay? So they can do their S1s in parallel, okay? But they have to do their S2 so oops, let's write this a bit nicer. So this is so everybody's doing S1 in parallel, okay? So this is S1 for iteration 1, right? This is S1 for iteration 2, and this is S1 for iteration 3. Okay. Let me erase the rest of this. However, they have to do the S2 statements in order, okay? So this means that S2 here has to on iteration 1 has to happen first, right? And then S2 on iteration 2, right? And then S2 on iteration 3. Okay. However, you see that you have a lot of parallelism in the S1 statements. Okay. And then next, we're going to do iterations 4, 5, and 6. Right. So we're going to have S1 of, let's say, 4, S1 of 5, and then S1 of 6. Okay. And this can be happening in parallel, but then you have to do the S2 statements, right, in order. Okay. S2 of 5, and then S2 of well, I can't write this anymore, but anyways, here you do S2 of 6, okay? Yeah, so then here you actually have a lot of parallelism, or actually at least a fair bit of parallelism for the S1 statements. Okay. Now, if you do it differently, okay, if you just have a static assignment, then what that's going to do is it's going to give the first chunk of iterations, okay? Let's say the first 10 iterations. It's going to give all of that to T1, okay? And then it's going to give the next 10 iterations to T2, and then the next 10 to T3. Okay. So in that case, you're actually going to, when you look at how the execution proceeds, you actually do not get any parallelism on the S1 statements anymore. Okay, because T1 itself is going to do the S1 statement for iterations like 1 to 10. Okay, and there's no parallelism there. Right, and then only after T1 finishes can T2 start. Okay, because T2, due to this to this statement over here, right? Let's see. Yeah, right. So then it's got to do these statements for the S2 statements. T2 has to do those only after T1 has finished all of its T1 statements, S1 statements. I'm sorry, I said that wrong. T2 has to only do its S2 statements after T1 finishes its S2 statements. Okay, sorry about that. Okay, so that is another example, and then let's just do one more of these. So suppose we have something like this, right? So again, the process is that we're going to look for the dependencies. So here you have some true dependencies. You have S1 to S3. You have a true dependence, but it's a loop independent dependence, right? Because here you write to AI, but then in the same iteration you read AI. Okay. You do have a loop carry dependence, so that is among this. That's within this statement over here. Okay, on the D. Okay. And then you have a an anti-dependence, and that is going to be let's see, S1 to S2. Right, okay, yeah, so here you read the B, and then here you write the B, okay? So there's an anti-dependence over here, right? And this is also a loop carry dependence. Okay, so for the ITG and the LDG, right? So because you have these loop carry dependencies from iteration I to I plus 1, then the LDG is, again, just this one big component over here, okay? However, we can again do some kind of loop fission over here, okay? So what you see is that there is no dependence between, so if you break the loop into two parts, the parts with the A, B, and C, right, and the part with the D, okay? So so we have these loop carry dependencies within the first part, right? Because there was this anti-dependence on the b variable from S1 to S2. Okay, so then therefore we need to do all of these iterations in sequence. Okay, and then there's also this dependence, loop carry dependence for the D. Okay, so then we need to do all of these iterations also in sequence. However, there is no loop carry dependence between these AVC statements and the D statement. Okay, so therefore we can do these in different orders. We can interleave them arbitrarily. Okay, and to represent that, we're going to put the first part in a section, right? The first three statements in a section, and then the other statement we're also going to put in a section, right? And these sections can actually execute in parallel. So each of the for loops within the section is going to execute sequentially, but the two sections can be interleaved. Okay, so that is these techniques of loop fission. And so next, we're going to talk about another technique called loop skewing. Okay, so this is actually going to transform the loop. So to talk about that, I'm first going to introduce some notations. Okay, so first I'm going to introduce this thing called distance and direction vectors. So now let's so now we're going to so previously we were using well, actually let's let T1 and T2 be two different iterations. Okay, and suppose that there's some sort of dependency from T1 to T2. Okay, we don't care what kind of dependency. So then we can represent, so T1 and T2 are both represented as vectors, as we saw, right? Like these vectors tell you the iteration that you're actually in. So then we're going to define this distance vector to be just the vector for T2 minus the vector for T1. Okay. So for example, oh, right. And then the direction vector is just going to be the distance vector, but you just take the sign of that. Okay. So as an example, so suppose you have a loop like this, right? Then what you have is that iteration ij is going to depend on iteration I minus 1 and then j plus 2. Okay. So there's a dependence from this iteration. From this iteration to that iteration. Okay. So then the distance vector is just going to be this the iteration like ij minus this iteration I minus 1 j plus 2. Okay, and if you do that, right, you're going to get distance vector is going to be 1 here and then negative 2 over here. And then the direction vector is just going to be the sign of this, right? So this is positive and this is negative, so that is going to be the direction vector. Okay, another example, so suppose you have something like this, right? So then here, iteration ij actually depends on two different iterations, okay? It depends on iteration I minus 1 j, and then also ij minus 1. Okay. So then in that case, the distance vectors are going to be, for the first dependency, you have this ij minus this thing is going to be 1, 0, right? And then for the other dependency, ij minus this thing is going to be 0, 1. Okay. And the direction vectors are, so this is positive and this is 0, and this is 0 and this is positive. Okay, so that's what these direction and distance vectors are. And now what we're going to do is, suppose we have a loop, okay, over loop variables I and j, right? And let's say that j is the inner loop and then I is the outer loop. Okay, so so basically, let's say that you have a situation like this, right? So so I is going to be the outer loop over here, and j is the inner loop. Okay. Now we claim that there are certain direction vectors that are legal, okay, and other ones are not legal or impossible. Okay, so we claim that these 5 direction vectors are possible, and all of the other ones are not possible. Okay, so what we mean by that, yeah, so these other 4 remaining vectors are not possible. Okay, so there are 9 overall, and 5 of them are possible, and 4 of them are not. Okay, so what we mean by that is now, since j is the inner loop, right, then if you look at all of these iterations, okay, so each of these dots here is an iteration, and if you look at all of them, then the order that you perform these iterations is that you're going to take the first value of I and go through all the values of j. Okay, so this is basically your iteration traversal graph, the ITG. Okay. And then you're going to go to the next value of I, and then you're going to go through all these values of j, right? And then like that, okay? So let me draw this a bit nicer. Okay, yeah, so we iterate through all of these iterations, and we do it in the zigzag order where you go column first. Okay, now why do I say that some of these direction vectors are possible? Okay, well, basically the only time you can have a dependency is so if let's say iteration t1 depends on iteration t2. Okay, then you have to do t2 first, and then you can do t1. Right, because t1 depends on t2. Okay, so the only time that you can have a dependence is if if t1 depends on t2, t2 has to happen first. Okay, so for example, this dependence over here. Okay, the negative, the plus negative dependence. Okay, so I'm going to erase this stuff, but just remember that we're going sort of in this zigzag order over here. Okay, now this is possible because we're going to do this iteration first, right? And then later on, we're going to do that iteration. Okay, so there can be a dependency from, oh, I'm sorry, I drew that wrong. Yeah. Okay, so there can be a dependency from here to here. That is okay. All right. Likewise, right, there can be a dependency from here to here, okay? Because we're going to do this iteration first, right? And then we're going to do this iteration first, and then that one. Okay, so that is okay also, right? And yeah, one more example, right? So since we're iterating in this direction, right, then we're going to do this one first, and then that one. So this dependency is also okay. Okay, however, you notice that some of these dependencies are not okay, right? So for example, this, let's see, negative plus, okay? So that would mean what? That would mean something like this, okay? So this would be a negative plus dependence, okay? And this is not possible because we're gonna do the zigzag order is that we're gonna do this, right? We're gonna do things in this order, okay? And so this means that this iteration over here, okay, needs to have some data from this iteration, okay? However, this iteration on the right is going to happen after the left iteration, okay? So there's no way for this left iteration to read anything from the right iteration, okay? It cannot depend on the right iteration because the right iteration is going to happen later, okay? The ij iteration happens before the I plus 1, j minus 1 iteration. Okay, so that's one of these things that's not possible, and then you can check that all of these other directions are also not possible because they would imply that an earlier iteration depends on something from a later iteration. Okay, so we have these legal or possible directions, and then we have some other illegal ones. Okay, so now we can talk about this technique called loop skewing. Okay, so this is going to use these direction vector concepts. Okay, so basically the idea is that sometimes you get this loop, and it looks like using our previous techniques of like loop fission and other things, even if we apply those techniques, we cannot get any parallelism out of something, a situation like this. Okay, so here we have this loop over here, right? So these are 4 loops. And what you have is that iteration I, so we have these 2 loop indices. So I1 is the outer one and I2 is the inner one. Okay, so so we're actually going in this order again, right? Okay, and the situation is that this iteration I1, I2, okay? So this is going to both depend on iteration I minus 1, I2, right? And also iteration I, and then I2 minus 1. Okay, and now if you look at this, it seems like there's no parallelism, okay? Because everything is in one big component, okay? If you try to parallelize over the I loop, right? Well, you can't do that because if you parallelize over the I loop, okay, so you try to do these different I2s in parallel, okay? So for example, you try to do this I2, you try to put these into onto different processors, okay? well, this you can't do because, for example, this statement, right, depends on this statement. Okay, and if you put these on different processors, you cannot enforce that this statement and this statement, this statement is going to happen after this statement. Okay, and likewise, you can't parallelize across the I1 loop, right? Because if you try to parallelize this way, then again you have these dependencies, and you have no way of ensuring that this statement is going to happen after this statement. Okay, so it looks like we cannot parallelize on either the I1 loop or the I2 loop. Okay, so it looks like we don't really have loop parallelism over here. Okay, however, the way loop skewing works is that we're actually going to sort of skew the way that we look at these iterations. Okay, so now imagine that instead of looking at these iterations in these orthogonal directions, okay, so imagine that you look at them in a skewed way. Okay, so basically we're going to do this iteration first, right? And then these two iterations, now notice that these two iterations are actually independent of each other, okay? Because as long as we do these two statements after this statement, okay? If we do these two things after this one, right, then we can do these two statements in either order, okay? Because this statement, for example, just depends on this one, and this thing depends on this thing, right? But they don't depend on each other, okay? So therefore, they can be done in either order, okay? So yeah, so right, and then let's see, and then these statements, right? The two and these statements, okay, these three of them, they're also independent of each other, okay? As long as you do these two statements first, before the other three statements, then these three can happen in any order, okay? So what you see is that overall, if you look at this loop in a skewed way, right, then for each of these diagonals, okay, all of the statements on the diagonal are independent of each other. Okay. However, you have to do the diagonals in the order of the diagonals. Okay, so you have to do the first diagonal, all the statements on the first diagonal before you do all of the statements on the second diagonal, before you do all of the statements on the third diagonal. Okay. So there's dependencies between these different diagonals, but within each diagonal, there is no dependence. Okay, so because there's no dependence within a diagonal, then now we can parallelize across these. Okay, so that's the basic idea of this loop skewing. Okay, now another way, so now we can sort of look at the previous situation another way. Okay. So we're going to go from, so we're basically going to transform the loop indices. So in the original formulation, in the original loop, you have loop indices I1 and I2. Okay, so you have these I indices. Now we're going to transform these to new indices K1 and K2. Okay, so the K indices. And what we're going to do is that we're going to say, so for the K, so now we're going to form a nested loop over the K1 and K2 indices. Okay, so it's going to be something like for K1, okay, and then for K2, okay. For K1 equals 1 to something, right, to X, right, and then for this also 1 to something to Y, let's say, okay. But we're going to have, we're going to transform the I loops to the K loops. And now we're going to say that, let's see, so, yeah, so now we need to do all of these outer iterations sequentially, okay? However, so this is going to be sequential, but this we can actually parallelize, okay? Okay, we can parallelize over the inner K2 loops, but we're going to do the K1s sequentially, okay? So so the way to see this is that you know, as long as we do this sequentially, then we're going to do this first, right? And then when it comes time for K1 equals 1, right, then for the different K2 instructions, or sorry, iterations rather, right, these iterations can be done, they don't have dependencies on each other, so they can be done in parallel. Okay. Likewise, over here for K2, for K1 equals 2, right, we have these three K2 iterations, and they can also be done in parallel because they do not depend on each other. They only depend on the stuff from K1 equal. So all the k1 equals 2 stuff only depends on stuff from k1 equals 1. Okay, now, yeah, so therefore, what we can do is, yeah, so then we can parallelize across this, right? Okay, so now the way that we can represent this, okay, the situation of looking at the loop in a skewed way is we can use some linear transformations to represent this. Okay, so we're gonna look at unimodular linear transformations. So the linear transformation can be modeled using, can be represented using a matrix, and a unimodular linear transformation means that the matrix is gonna have a determinant of either -1 or 1. Okay. And basically, the reason we have to use unimodular linear transformations is because after you transform this loop, these loops, right, then you need to make sure that all of the iterations you did for the I iterations, right, every one of them you have to also do in the k iterations, right? You can't skip any work. Okay. The only thing you can do is you can try to do these I iterations in some different order. Okay. Now that different order still needs to preserve all of the dependencies in the I graph, right? So once you move to the k graph, you need to preserve all of these dependencies. And furthermore, you have to do everything in the I graph you also have to do in the k graph. Okay, so this is why you use these unimodular linear transformations, because they can ensure that all of the iterations in the I loop, right, get mapped onto some iteration in the k loop, so you don't skip anything. Okay, so then now we're going to go for a unimodular transformation to represent this loop skewing. Okay, so the matrix we're going to use is this matrix U over here, right? And so this is a unimodular matrix because you know it's a lower triangular, and then the determinant is just the product of all of these diagonal values. And the way that it works is that if you start with an iteration I1, I2, right, then when you look at these k iterations, okay, so what is actually being done in iteration k1, k2, okay, this is actually this k1, k2 corresponds to what was done in let's see, so for example, this iteration, right, corresponds to this iteration over here. Okay, this one, right, corresponds to this one. Okay, this one corresponds to that one. Okay, so there's just a one-to-one correspondence between the I1 iterations and the I2 iterations. Okay, and also whenever you have let's see, so whenever you have an I1, I2 iteration, okay, this is going to get mapped onto a K1, K2 iteration. And what is that K1, K2 iteration? It's going to be I1 plus I2 and then I2. Okay, so for example, this iteration over here, right? This has a corresponding iteration in the among the k iterations. And so what you're doing is you're taking this thing, which is iteration 1, 2 in the I space, right? And then you're mapping this to something which is, let's see, you're mapping this to 3, 2, okay, in the k space, okay? And this 3 here, you get this by just taking the I values and adding them, okay? Right, so this 3 here is 1 plus 2, right? And this 2 here is just the 2 over here, okay? So for every iteration in the I space, when you apply this matrix U to it, right, you get the corresponding iteration in the k space. Okay, now there are several things that we need to ensure about this transformation. So we need to ensure that all of the dependencies are, well, first of all, we need to ensure that all of the same work is being done in the I iterations as the k iterations. Okay, so the same computations are being performed. And this is true because you see that, you know, so the first I iteration, right, is going to get mapped to the first k iteration, right? And then after that, since we're doing, you know, these two things after we do 0, okay, you see that in the k iterations, right, these are going to use the same data and get the same values in the k iterations as in the I iterations, right? So for the I iterations, you're going to get the data this way, right? And in the k iterations, you're also going to get the data this way, right? And since we've already computed this node 0 here in both the I and the k iterations, then these two nodes, right, are going to obtain the same value whether we're using the I iterations or the k iterations, okay, whether we're on the left here or whether we're on the right. Okay, so these two guys get the same values, right? And now you can check that these guys, these three nodes, okay, or three iterations, okay, they also get the same values both in the I iterations and the k iterations, okay? And you can do that inductively because, you know, these nodes get have the same value on the left and on the right. And so if they have the same values, then, for example, this guy, he's going to get the same value on the left and on the right because his values are going to come from this one and then that one, right? And then over here, it's also going to come from the same two iterations, okay? Yeah, so so therefore we compute the same values and we perform exactly the same computation in the I iterations and the k iterations, okay? The only difference is that we do things in a different order, okay? But the final outcome is going to be the same in both the left and the right. Okay, right. So yeah, so in fact, another way to see this is that you have these dependence vectors on the left, okay? So for example, in the I iterations, right, we have this dependence vector, so this is what? This is 1, 0, right? Okay, because 1 represents the outer loop index, okay? And then this is a 0, 1 over here, right? So what you see is that the 1, 0, right, gets mapped, gets changed to this kind of dependence, okay? So this is still a 1, 0 dependence over here, okay? But the 0, 1, right? So this is going to get mapped to a let's see. So yeah, so the 0, 1 is going to get mapped to this vector over here, and this is a 1, 1 dependence. Okay. Now both of these dependencies are legal, okay? Because we talked about the set of legal dependencies, and so we said that for example, if we go back a few slides, right? So the 1, 1 dependence, right? So that's corresponds to like the plus plus direction. Okay, so that's legal, right? And then the 1, 0 thing corresponds to plus 0. Okay, so that's also legal. Okay, and basically it's because, you know, when you do this iteration, right, then you've already done these two first. Okay, so it's fine to do this. It's fine for this thing to depend on these two iterations because we're gonna iterate through everything in this order. So let's actually draw out the order. So we're gonna go in this order. Oops. Wait, wrong. Right, we're gonna go in this order. Okay. Yeah. And so it's fine for this statement to depend on these two ones because they were, it's fine for this statement to depend on these two ones because they were done earlier in the execution. Okay. All right. So yeah. And so the other thing is that we can. So the direction vectors here, they were. So we had direction vectors plus 0, right? And then you had a direction vector 0 plus, right? And so this got transformed to another plus 0, right? And then this thing actually got transformed to plus plus. Okay. Now notice that both of these, so this is in the I space and this is in the K space. Okay. Now notice that in the K space, both of these direction vectors are positive in the, so this is the K1 coordinate, right? And this is the K2 coordinate. Okay, so they're both positive in the K1 coordinate. K1 is like the outer loop. Okay, so yeah, so you have K1 is the outer loop, and then K2 is the inner loop. Okay, so because they're both positive, okay, then what this means is that when you're doing a particular K1, okay, then let's say K1, you're doing this iteration, okay, K1 equals 3, okay. Because these dependencies are positive in the K1 coordinate, then that means that these things are, the K1 equals 3 iterations are only depending on things from k1 equals 2 or 1 or something less than 3, okay, because they're positive over here. Okay, now in fact, they only depend on the k1 equals 2 part. Okay, but they could also depend on, k1 equals 1 or whatever. Okay, right. But as long as they're positive, then they're only depending on k1 equals values smaller than 3. Okay, and so that means that when you have k1 equals 3, you can actually do all of these k2 iterations in parallel, because each of these, for different k2s, right, they're only depending on something with a smaller k1. And we know that we've already executed everything with smaller k1s, right, because we execute things in order of the k1s, right? So you only start the k1 equals 3 part after you're done with the k1 equals 2 part. Okay, and when you do the k1 equals 3 part, you're only depending on things for the k1 equals 2 part, and you've already finished all of those, right? And so, so therefore, you can do all of these computations in parallel. Okay, so what this is, to sort of summarize this, this is saying that if you have this coordinate, for example, k1 over here, okay, where everything is positive, okay, then this means that you need to do this k1 stuff in sequence, right? k1 equals 1, 2, 3, and so on. But you can do all of the k2 stuff in parallel. Okay. All right. So so now we're gonna try to summarize these sort of two statements that we made. So the first thing is that when you transform this loop using this unimodular U thing, okay, you have to make sure that the transformation is going to be legal, and you want it to be parallelizable. Okay. Now we saw that it was legal because you transform these direction vectors into these new direction vectors, and all of these new direction vectors are legal. Okay, so so we can make a theorem out of that, which is that if we have a unimodular transformation, right, and if you apply this to go from like the I iterations to the k iterations, and if all of the distance vectors in these k iterations, if all of them are legal, okay, then you have a legal transformation. Okay, then it's actually okay for us to transform from these I iterations to these k iterations via this U matrix. Okay, right? Yeah, so so again, if you actually do the computations, right, so the U equals this, right? So one of the distance vectors in I was this 0, 1 thing, right? And if you transform that, you get 1, 1. And the other dependence vector in the I iterations was 1, 0. If you transform it, you still get 1, 0, right? And so then the direction vectors are, so this is going to be plus plus, and this is plus 0. Okay, and both of these are okay. So our transformation U is okay. Now this is summarizing the second thing about what we said, which is that if you have one of these coordinates, right, the k1 coordinate, right, if all of these are positive over here, okay, then you can actually parallelize on all of the lower coordinates. Okay, so here you just have you have 2 for loops, right? You have just a singly nested for loop, right? However, you could imagine that there are more coordinates over here, like k3 or something. Okay, but however many coordinates you have, right, you can actually parallelize across all of these, as long as you ensure that here you have a coordinate which is all positive. Okay, so you find one of these coordinates which is all positive, and then everything, all of the iterations, so this is like an outer iteration, and all of the iterations inside of that, okay, all of the inner iterations after that point, right? So here you have the outer iteration and all of these inner iterations, so you could have another k3 here and so on, right? These can all be parallelized. Okay, and so yeah, so this is what we have over here, right? So we have that previously you had a loop like this, right? And then now this gets transformed to this kind of under U, this gets transformed to this, right? And then you see that this can be parallelized because once you since we're going in the order, since k1 is the outer loop, right, and we're doing all of these in sequence, then once you finished some k1, then for the next k1, right, you can do all of the different k2s in parallel. Okay, so yeah. Okay, yeah, so this is talking about what kind of loop transformations you're allowed, what kind of loop skewing you're allowed to use. Okay, so we have to use a unimodular matrix, right? So that we actually do the same number of iterations in the original space and the new iteration space. And all of the distance vectors, so the first theorem is saying that all of the distance vectors need to be, or the direction vectors need to be legal, okay, after the transformation. Okay, and the another property that you want is, well, the point of doing the transformation is to parallelize, right? So when can you parallelize? Well, you can parallelize when, if you look at the direction vectors for a loop, right? So if there's some ith coordinate, okay, where all of the direction, where it's positive, where it's all positive in the ith coordinate, okay, then for all of the loops deeper than level I, okay, so like for K2 and maybe K3 and so on, right, you can run all of those in parallel, okay? So we are basically trying to look for these U's, which are unimodular, right? They're legal, and they give this property that they produce some coordinate I, which is all positive, okay? Because once we have that, then we can parallelize in all of the deeper layers. Okay, now something else we have to figure out is, so once you go to these k iterations, right? So what data is actually being accessed in the k iterations? Okay, so now when you have these I iterations, right, you're going to map these to the k iterations via this U matrix, right? So then you can just multiply by the inverse of this, and you get that if you're in this k iteration, right? What is which I iteration does that correspond to? Well, you just multiply by the inverse of U. And so you get that, for this k iteration, this corresponds to this I iteration, okay? And so therefore, in this k iteration, the data that you're accessing is actually from this iteration of the original loop, okay? Because we know all the data accesses in the I iterations, right? Because, like if you... yeah, so like we have this program here, right? And this is the original program. This tells us all the data accesses in the I iterations, okay? And now we have to figure out what the data accesses are in the k iterations, right? But since we know the mapping between the I and the, we can map back from a k iteration to an I iteration, and then we look in the I iterations to see what the data accesses are, okay? And that tells us what the data accesses are in the k iteration. Okay. Yeah. So okay, right. So we go from the k iteration back to the I iteration, and then we look at the data accesses in the I iteration, and then we get the data accesses. So so as an example, if U equals this, right, then U inverse is going to equal that matrix. So for this k iteration, that corresponds to some I iteration, right? And so this is actually going to be equal to, so I1 here is going to be equal to K1 minus K2, right? And I2 is equal to K2. Okay. And now what we know is that in iteration I1, I2, right, what we accessed was we accessed A of I1 minus 1, I2, right? And then A of I1, I2 minus 1. Okay. And now this thing here, the I1, right? This is equal to K1 minus K2, right? This is equal to K1 minus K2, and this here is equal to K2, okay? So therefore, that means that in this iteration, right, we were accessing K1 minus K2 minus 1, okay? And then in this iteration, right, we were accessing K1 minus K2, and then K2 minus 1, okay? So that tells you that in this, right, yeah. Okay, and then finally, you notice that the bounds of the loops are going to change when you go from the I to the k iterations. Okay, so if we go back to this picture here, right? So the bounds of the loops are so it's going to be 0, 3 here, and then 0, 3 for both I1 and I2. Okay, but here, right, you see that K1 is actually going to go from 0 to 6. Okay, and then K2, right, so its bounds actually change. Okay, so for example, initially K2 can only be 0, and then when K1 equals 1, this can be 1 or 2, right? So its bounds actually change. Okay, so we need to go compute the bounds for K1 and K2. Okay, so to do that, so this is the final thing we're going to do here, right? We're going to compute the loop bounds after you do this loop skewing. So now we have that, over here we're saying that I1 equals K1 minus K2, right? And then I2 equals K2, okay? And then also what we know is that so we know the bounds for the I iterations, okay? So I1 is between 0 to 3, and I2 also, okay? And so if you plug that in, right, so K1 minus K2 equals I1, so you get that this is between 0 to 3, right? And then K2 is also between 0 to 3. Okay, so so now since K2 is less than 3, you can just, at most this is going to be a 3 here, right? So so this tells you that at most K1 is going to be a 6. Okay, so K1 is between 0 to 6. Okay. And then also, yeah, so then you have, so if you start with this, right, then you get this inequality, right? So K1 minus 3 is less than K2, right? And also you have that that 0 is less than K2, okay? So so K2 is at least equal to K1 minus 3 and at least 0. So K2 is going to be at least the maximum of 0 and K1 minus 3, okay? And then you can use like a similar derivation, and you can get that K2 is going to be at most the minimum between 3 and K1. Okay, so it's at least going to be this and at most that. Okay, so so here we just sort of computed these things directly. Okay, so in general, so all this loop skewing stuff works for multi-dimensional loops. Okay, so here we have 2 dimensions, but you could have more dimensions. So you can imagine that this is if you do this directly, it's going to be very complicated in higher dimensions. But there's a general method called the Fourier-Motzkin method, which can let you compute all of these loop bounds. So after you do the loop skewing, your bounds are going to change, but then you can compute them using this Fourier-Motzkin method, which we're not going to talk about, right? So this, so the Fourier-Motzkin method, basically, it just it sort of automates this process that we're doing manually currently. Okay, so then now we're going to put all this stuff together. Okay, so now we've figured out that we have this transformation which is legal, right? It's parallelizable, right? So we looked at which data items are being accessed, right, over here, and then we looked at the loop bounds over here. Okay, so this means that we're going to do this entire transformation from the I iterations to the iterations to the k iterations. Okay, right, and in iteration k1, k2, right, we're going to be accessing this location over here, and we're going to be setting it equal to to this thing plus that thing. Okay, and this is going to be our loop bounds for k1 and k2. Okay, and then these 2 computations are going to produce the exact same outputs. Okay, so the A values are going to end up to be exactly the same after you do this this one or this one. Okay, and then furthermore, for this K algorithm, right, for the K loops, you can you're going to do the K1 sequentially, but you can do the K2. I don't know why that didn't work, but you can do the K2 iterations in parallel. Okay, so that is loop skewing. Okay, now the final thing we're going to talk about is so here we've been sort of transforming these loops in various ways to get more parallelism. Okay, but it turns out that sometimes there's nothing you can do to the loop to actually get more parallelism. Okay, sometimes you just have to change to a different algorithm to solve the same problem, of course, right? So you have a problem that you're solving with one algorithm, but whatever you do, you can't really parallelize the loops in the first algorithm. So then you try to switch to a different algorithm. Okay, so we're going to call this type of situation algorithmic analysis. Okay, because we're changing the algorithm to obtain more parallelism. So so now this is very specific to the problems that problem that you're trying to solve, right? So there are some problems where you can transform the algorithm and get better parallelism, but other ones, you know, it might not be possible to do this. Okay. Yeah. So one example where this where you could change to a different algorithm is that some algorithms are, for example, some of them calculate an approximation. Okay. So later on we're going to look at some iterative algorithms, and they try to compute some result, but it's an approximation. Okay. So because you're getting an approximate answer in those algorithms, then you can actually, even if you were to restructure the algorithm, right, you would end up with another approximation, but maybe both approximations are good enough. Okay, so in those situations, maybe you can actually change your algorithm and get still compute an acceptable answer, right? An approximation that is close enough, but you can do it in a more parallel way. Okay, so that's one example. But we're going to look at another example of this, a different example. So here we're going to try to compute the Fibonacci numbers. Okay, so the Fibonacci numbers are this. It's a sequence of numbers. So it starts out 1 and then 1, and then for the remaining values, it's going to be the sum of the previous two values. Okay, so I think you've seen this sequence before, right? So the sequence goes like 1, 1, 2, 3, right? So the 5 is equal to 2 plus 3, right? The 8 is equal to 3 plus 5, and so on. Okay, so if you compute this sequentially, right, then this is going to take you just linear time, because you can just compute this stuff one by one, right? 13 equals 5 plus 8, and so on. Okay, so now let's see if we can compute this in parallel. Okay, so so if you try to form the loop dependence graph for this, right? So you have a for loop to compute this thing sequentially. And then if you look at the loop dependence graph, right, that's going to, each iteration is going to depend on the previous one, and then 2 iterations back. Okay, so the loop dependence graph is going to look like this. Okay, and so this is all just in one big connected component. And so a priori, you don't have any parallelism here. And if you look at the loop over here, right, you also it's hard to do any changes to this loop to get any sort of parallelism. So it seems like this Fibonacci numbers, you would have to compute them sequentially, right? Because it's it looks like, in order to compute the nth value, you must have already computed the previous two values, right? And so it looks like you simply have to go in the order of these values in order to compute them. And so there's would be no way to parallelize this. However, it turns out that if you reformulate this problem, okay, if you try to apply a different algorithm to this, then you actually can get parallelism. Okay, and this this new algorithm is based on this very simple property. Okay, so suppose you take 2 consecutive values for the sequence. Okay, and let's say that you multiply by this little matrix here. Okay, so then what you get is that the first value of the output is going to be f of n minus 1 plus f of n minus 2, right? And that is going to be equal to f of n by the Fibonacci by definition. Okay, and then the second value here is going to be equal to just f of n minus 1. Okay, so what this shows is that you can go from 2 consecutive values of the Fibonacci sequence, and if you multiply it by this matrix here, then you get the next 2 consecutive values. Okay, and if you multiply by this matrix again, right? So now if you take f of like n and then n minus 1 here, right? Then you're going to get the next 2 values, right? You would get this. Okay, so in general, what this means is that if you just keep multiplying, if you start with, so let's let this matrix be, let's call it A. Okay, so then if you just start with the first 2 values in the Fibonacci sequence, right? Then as you keep multiplying by this A, you get these later values. So in fact, if you multiply this by A n times, you're going to get the n plus second and n plus first values. Okay. And so this shows that in order to compute these values, right, all you need to do is to compute A of n quickly. If you can compute A of n quickly, then you can just multiply that by this 1, 1 here, and that will get you the n plus second and n plus first values. Okay, so now the only question is, can we compute a of n quickly? And yes, we can do this. So we're just going to use a reduction tree to do this, right? So suppose that we're trying to compute a of n, and let's say that you have n processors, okay? So then each processor is just going to start with a copy of a, right? And then they're going to proceed up in this multiplication tree, okay, in parallel. Okay, so you're going to first pair up these processors, right? They're going to multiply their a's, and so here you're going to get a squares everywhere, right? And then you're going to pair them again, and they're going to multiply, and then you're going to get a to the fourth everywhere, okay? And then you do it again, and you get a to the eighth, okay? And so this basically shows that in order to compute a to the n, right, if you have m processors to start with, then after just log n of these steps, okay, you're going to compute a of n, right? Because the exponent of a keeps doubling every time you go up a level. Okay, so this shows that you can actually compute, if you have m processors, you can compute f of n in log n time, okay, just by computing a of n in log n time, okay, instead of the sequential time, which would be order n. Okay, so now, again, this depends on the problem that you're working with, okay? So other problems, maybe if you think about it hard enough, you can actually come up with other transformations from a very sort of something that looks like it's sequential. You can maybe transform that to something more parallel, okay? But there are problems that, even though people have been working on these for a long time, they still do not have a good parallel version of these algorithms, okay? So this, so this is a very problem-dependent technique. Okay, so that's all we have for this lecture. See you guys next time.